Alright, so this is a video for Math 1. We're looking at sections 2.2 and 2.3, linear and nonlinear functions. So starting by looking at linear functions. If you think of the word linear, linear has the word line in it. So I want you to think of that as we're talking about linear functions. Think of lines. Okay, so we kind of talked about dependent and independent variables. In a relationship between variables, the dependent variable changes in response to the independent variable. So the dependent variable changes because of what happened to the independent variable. So things that are usually independent are things like time, and time will change other things like speed or distance over time. So the independent variable would be time, the distance would be the dependent variable. Values, so let's see, values of the dependent variable are called outputs. And the values of the independent variable are inputs. So the outputs, the letter that we usually use when you think of graphing is Y. And the inputs are X. So essentially think X, those are your inputs, and those are your independent variables. Then the Y is your output, and those are your dependent variables. So you can kind of see there is a coordination between the I's. It might help you. Inputs are independent, outputs are, well, different letter, but okay, so let's look at an example. So copy this example down. If you need more time, you can pause the video, obviously. So in the diagram, what is the relationship between the number of rectangles and the perimeter of the figure that they form? Represent this relationship using a table, words, an equation, and a graph. So if we look at this figure, we've got rectangles here, and the rectangles each have a length here of 6, or a height, I guess that would be, of 6, and then a width of 1. So 6 is always the same. Then the number of rectangles also changes. We have the number of rectangles, and as we go up with rectangles, we're looking at what happens with the perimeter. So we're going to start by looking at this in a table. So think about what is independent and dependent here. Well, we have number of rectangles is one thing that we're looking at, and the other thing is the perimeter. So the number of rectangles is really changing what the perimeter is doing. So I'm going to let X be the number of rectangles. That's our independent variable. And Y is our perimeter. So the perimeter changes as we add more rectangles. So if we do a t-table with one rectangle, let's get the perimeter here. We have 6 on this side, 6 on this side, 1 and 1. So it becomes 2 times 6 plus 2 times 1, which gives you 12 plus 2 is 14. So that's our perimeter. With two rectangles, we have 6 here, 6 here, so there's 2 6's, plus, well, let's see, how many 1's do we have? We have 1, 2, 3, 4 1's. So I'm going to say there's 4 1's. So that gives me 12 plus 4, which is 16. Then we have 3 rectangles. So we have a 6 here, a 6 here. So we have again 2 6s. And then we have how many ones? 1, 2, 3. And then there's 3 more on this side. 4, 5, 6 ones. So that gives us 12 plus 6, which is 18. So then one more. We have 4 rectangles. That gives you 6 here, 6 here. So again, we have 2 6s. You notice a pattern with the 6s? We're only having 2 6s. But the number of ones change each time. Let's see, here we have 1, 2, 3, 4, 5, 6, 7, 8. 8 ones. So then that gives me 12 plus 8, which is 20. Okay, so that's looking at the information in a table. Let's look at it in words. What's happening? Okay. Well, let's just compare these. All of these have 12, right? 14 gave us 12 plus 2. So it's like the 12 never changed. It's always a 12. So then compare the 2, 4, 6, and 8. How do those numbers relate to the 1, 2, 3, and 4? Well, they're double. So we could say the perimeter is 12 plus the double of the number of rectangles. Right? If the number of rectangles was 1, then we're adding 2. If the number of the number of rectangles here was 1. So then the number of rectangles here is 1, so we're adding 2. The number of rectangles was 2, so we're adding 4. The number of rectangles here was 3, we're adding 6. The number of rectangles was 4, so we're adding 8. Okay, so then let's write this as an equation. So we can see that y, the perimeter, is going to be equal to 12. Everything had a 12 in it. Those are the 6s on the side. 6, 6, 6, 6. Plus 2 times the number of rectangles, which is our x. Okay, and there's an equation. So now we're going to look at a graph. Let's make a graph of this. So I'm going to make some room here. And so we're going to look at, when we make the graph, we're not going to need a full x and y axis, right? Because we're just looking at positive things. And we're not going to look at what happens at 1.5 or 2.5. We're only going to look at 1, 2, 3, and 4 because we're counting the number of rectangles here. Okay, so we're going to make a little graph. So it's just the first quadrant. We're looking at x and y, and we're going to label it because we want to know what these things are. So x was the number of rectangles, and y is our perimeter. Okay, so let's mark this. At 1 rectangle, 2, 3, and 4, we have the first one, we have a perimeter of 14. So I'm going to go, now there's a little trick when you make a graph. If you want to start like right here, let's say I want to start at 14, then you make a little zigzag here. And what that means is that we skipped some things. And then let's go 16, 18, there's 18 in there, and 20. So then we're going to put some dots. At 1, we get 14. At 2 rectangles, we have a perimeter of 16. At 3, we have 18. At 4, we have 20. And so if you look at the graph that we have, this is a linear relationship because it essentially makes a line. right? It goes in a straight path. It could be going up as a straight path. It could be going down as a straight path. This one is obviously going up as a straight path. We could see it following a linear pattern. Okay, so let's look at what a function is. This is a very important word. So we could describe the relationship that we saw in pattern 1 by saying the perimeter is a function of the number of rectangles. A function is a relationship that pairs each input with exactly one output. Alright, so we put an input out. So you put one input, which is our independent variable. The function does something to it, and then our output, we get exactly one output. If ever a function, when you plug, or if ever you put something in and you get 2 or 3 or more than one outputs, then it's not considered a function. So a function has exactly one output per input. Now a linear function is a type of function. So it's a type of function whose graph is a non-vertical line or part of a non-vertical line. So non-vertical means not straight up and down. If you have a straight up and down line, that doesn't work. But all other kinds of lines. So here's our x and y axis. Here's a line. That's non-vertical. That's a linear function. There's another one. You can even have it go horizontal. Those are all fine. Just not straight up and down is all it's saying. Alright, let's look at example 2. Photography. The table shows the relationship between the number of photos x you take and the amount of memory y in megabytes left on your camera's memory chip. Is the relationship a linear function? Describe the relationship using words, an equation, and a graph. Okay, so they gave us the table here. So you have a memory card and it's 512 megabytes when there's no photos on it. Okay, you take a picture. Okay, there's now 509 megabytes. Then we take another picture. There's 506 megabytes. So now we have 3 pictures on there. We have 503 megabytes. So to determine if it's a linear function from a table, what you want to do is identify, is y changing at a constant rate while x is changing at a constant rate. They don't have to be changing at the same rate. So at a constant rate. But they need to be changing consistently. So what I mean by that is, if you see, we're going up one picture, so up 1. Then we go up another picture, so up 1. Going up one picture, so up 1. So you see, for every time we take a picture, we're going up 1. So then what is the memory doing? Well, it's going down. We're subtracting 3. Then we're subtracting 3. Then we're subtracting 3. So we can see, as this changes up 1, this is always changing down 3. That's creating a linear pattern. So let's look at a graph. So for this one, I need to get up to 512 megabytes. So I'm going to use that trick where I do a little zigzag here that says I'm skipping a lot. So then I'm going to start 500. Let's do 5. Let's see, I need to get to 5. Let's see, so I'm going to do 5. I'm going to go by 2s. 502, 504, 506, 508. I might have to go a little bigger. 510, and then 512. Okay, so this is megabytes. That's our Y. And that is dependent upon how many pictures we're taking. So for X, 0 pictures here is going to be 512. 1 picture is going to be 509. 2 pictures is going to be 506. 3 pictures is going to be 503. So you see that as it's going down 3 megabytes for every 1 picture. Down 3 megabytes for every 1 picture. So it's consistent. So how would we relate this in words? For each picture taken, the memory goes down 3 megabytes. So that's words. Okay, now the other thing we got to do is create an equation. Alright, so let's create an equation from this. Now remember, X is our pictures, and that's our independent variable, and Y is our output, which is our dependent variable, and that's the number of megabytes left on the card. So let's think, we started at 512 megabytes. Then we subtract 3 megabytes for every picture. So X is the number of pictures. If we multiply that times 3, it tells us how many we're subtracting. How much we're subtracting, right? So if you have like 10 photos, then you used to be subtracting 30 megabytes. If you're subtracting 1 photo, then it would just be 3. So that is our equation. Alright, let's talk about nonlinear functions. So generally, you can think of a function as a rule that you apply to the input in order to get an output. Alright, so nonlinear is just what it sounds like. It's not a line. Okay, so we'll do other things to it. So let's look at this first example here. The table shows the relationship between the number of steps in a staircase below the number of and the number of blocks needed to build the staircase. Okay, so we have steps here, and then so for this one step, you see there's actually 1 block, 1 long block here. So 1 step, 1 block. Alright, so we put it in a table. 2 steps, so you have 3 long blocks. Right, this only counts as 2 steps because you go up 1, then you go up a second time. Alright, so we need 3 blocks. For 3 steps, we have to go, there's our 3 steps. If you count the blocks, there's 1, 2, 3, 4, 5, 6 blocks. So then, what do we think is going to happen with 4 blocks, or 4 steps? Do we see a pattern here? Okay, well let's draw it. Alright, there's 1, 2 steps, 3 steps. It might be easier if I draw it like this, more sideways. So there's 3 steps, there's 4. So if we count it down, you can see the blocks. So then you can imagine this 3-dimension. Yeah, that looks a lot better. Okay, so how many blocks, remember they're long blocks, do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 blocks. So that gives us a point of 4, 10 as an ordered pair. So then 5, well, let's see if we can figure out a pattern here. We can try doing what we did before. We're going up 1 step, so plus 1, plus 1, plus 1, plus 1. Is it going up by 1? This one up by 2. This one up by 3. And then from 6 to 10 it goes up by 4, so it's not going consistently. But there is a pattern here, right? We see that it's going 2, 3, 4. So the next one, you could say, well, what is it? It's probably going to be 15. Right? We can check that. 1 step, 2, 3, 4, 5. And then we draw our blocks. Alright, so 1, oh wait, did I get them all? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. Okay, so this is not linear though. It's not going up 1 each time. And it has to do with the fact that as we add the 5th step, we had to add all of this whole row of blocks here. Right? With the 4th, we had to add 4. So each time we're adding a whole row. So if I do 6 steps, I'm going to have to do 6 more. So is this a function? Remember, a function is one input gives you exactly one output. So if I plug in 1, if I have 1 step, there's only one answer. It's 1 block. I'm not getting 2 separate answers. So no, there's no problem here. It is a function. Yes. Okay. It's a function because only one input or output per input. Alright, let's look at another example. The area A in square inches of a pizza is a function of its radius r. Graph the function shown by the table. Is it linear or nonlinear? So we're going to make a graph. So our independent variable is r, which is the radius of the pizza, because the area or the size of your pizza is going to depend on the radius. So let's see. I'm going to go by 2's because they are 4, 6, 8, 10. I guess I didn't need that much space. Okay, and then for I got 12.57 up to 314.16. So I'm going to have to go by something a little weird. I'm going to go by 20s. So 20, 40, 60, 80, 100. Let's see if I can make it. 120, 140, 160, 180, 200. 220, 240, 260, 280, 300. Okay. And then 320. So with 2 inches, so inches here, and this is area, so this is inches squared, and 2 inches, you have 12.57. So I'm going to go somewhere in here. In 4 inches, it goes to 50, so that's somewhere in here. In 6 inches, it goes to 113. So that's a little bit right here, just estimating. In 8 inches, I get to 201.06. Okay. It's about here. In 10, I go 314. It's about here. That's a little high. So you can see it's not exactly doing a line. Like a line would be like this. It curves. It goes higher. So this is non-linear. Alright. Oops. Go back to number 3. So the table shows the number of blocks in each figure. Alright, so we have 1 block. This is a block with, okay, so it's looking at the edge, the number of blocks on each edge versus the total number of blocks. So this is the edge, 1. This is the edge, 2. This is the edge, 3. So if we count, 1 block or 1 edge is just 1 block. 2 would be, let's see, there's going to be 1, 2, 3, 4, 5, 6, 7, 8, and there's one you can't see behind here. That's the 8. And then the 3 gives you 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's this whole row in the middle. 10, 11, 12, 13, 14, 15, 16, 17, 18, and then we have 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, so it's 27. So this one you kind of have to imagine like a Rubik's Cube. Well, if we drew out, well, let's just look at what's happening. What's happening to the 1, to the 2, to the 3 to get these numbers? These are called cubes because we are actually cubing things. So to cube something is to take it and multiply it times itself 3 times. And so what's happening is we're cubing this x. 1 cubed is 1. 2 cubed is 2 times 2 times 2, which is 8. 3 cubed is 3 times 3 times 3, which is 27. So then this is going to be 4 cubed, which is 64. 5 cubed, which is 125. Okay, and then so an equation would be y equals x cubed, where x is the edge. And then to graph that, we're going to have to go way up, right? We're going to have to go into the hundreds. So let's go by 20, 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, that's a really messy graph. Do better than that. So 1 is 1, so that's like way down here. 2 is 8, that's like barely higher. 3 is 27, so we're like almost up to 30 now. 4, 64, so 10, 20, 30, 40, 50, 60 is right here. So you can see it's curving, it's non-linear. And then 5 is 125, so we're like way up here. So you can see there's a curve to it. So this is an example of a non-linear. Okay, last example. The ordered pairs 1, 2, 2, 4, 3, 8, 4, 16, 5, 32 represent a function. What is the rule that represents this function? Well, x, y, 1 goes to 2, 2 goes to 4, 3 goes to 8, 4 goes to 16, and 5 goes to 32. Basically, if you look at it, these are multiples of 2, right? This is 2. This is 2 times 2. This is 2 times 2 times 2. This is 2 times 2 times 2 times 2, if I just multiply it by another 2. And then if you keep going, this is 5 2's. These are powers of 2. So that could be written as 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So really, it's y equals 2 to the x. Alright, we're done.